Hello, everyone, and welcome back to the main stage and the second half of today's presentation agenda. Now, before we move on to the second half of our agenda, I'd like to take a moment just to thank all of our sponsors once again for their support today. And I'd also like to remind all of you to stop by their virtual exhibition booths to access a wide range of resources, insights, and exclusive material. Now, in part 2 of Global Hydrogen Conference, we have two excellent presentations coming up. So up first, we have a presentation from Jack Samways, Business Development Manager, New Energy Europe at MSA Safety. Jack will examine key safety considerations for hydrogen production, storage, and refueling environments, focusing on a multi-layered gas and flame detection approach. The presentation will provide practical insights to help strengthen safety programs and promote more effective risk management in hydrogen applications. Once again, we'll have a live Q&A session straight after the presentation, so please submit your questions as we go along via the chat and Q&A tabs. So, without further ado, I'll pass the floor to Jack.
Good morning, everyone. Thank you for joining. I'm Jack Samways, the Business Development Manager for New Energy here at MSA Safety. MSA is a global safety company with 5,000 employees operating in 100 countries and generating $1.8 billion in annual revenue. Our mission is simple: safeguarding people, places, and the planet, and hydrogen safety is a major part of that. Today's session will be focused on how we approach hydrogen detection, not just through products, but strategy, combining standards, technology, and practical design to keep those systems safe. This is the agenda for today. So we're going to look at the properties of hydrogen, the regulatory requirements, the layered approach that MSA offer, and an application example, and then we'll conclude. So beginning with hydrogen properties. When we talk about hydrogen, it's not a new discovery, but what's changed is how and why we use it. It has the highest energy per kilogram of any fuel, which makes it particularly valuable for weight-sensitive sectors such as aviation and heavy transport. The trade-off is that it has a low energy per volume, so we compress or liquefy it, and that introduces very different safety and detection requirements that we'll explore later on. Refueling speed is one of hydrogen's big advantages. At 350 or 700 bar, we can fill a heavy-duty vehicle in under 10 minutes, giving the same operational convenience as diesel, but with zero emissions at the point of use. And finally, hydrogen is not only an energy source, but a carrier too. It links power generation from renewables with sectors that cannot be electrified. This means we're seeing more facilities from production plants to refueling stations where hydrogen is stored and handled at scale. In those environments, robust detection becomes one of the most important safeguards. There are some challenges that most of you may be aware of, but it's still worth revisiting. What makes hydrogen so unique as a gas? Hydrogen itself is colorless, odorless, and completely invisible when leaking, which is why detection plays a critical role throughout that. One question that often comes up is why can't we add odorant like we do with natural gas? The reason is chemical stability. Hydrogen reacts with most sulfur-based compounds that would normally provide a smell, so we can't safely add anything without compromising purity or creating other risks. When it comes to the flame, the challenge is the invisibility and the nature of the heat they emit. A hydrogen flame burns over 2,000 degrees Celsius, but because of the very low thermal radiation, you won't feel that heat until you're dangerously close to it. So it's not just invisible, it's deceptive. You could be standing right next to the flame and not realize until it's too late. This slide looks at some of the challenges that most people don't usually consider when it comes to hydrogen leaks. The diagram shows a 2 millimeter leak at 100 bar and how the gas plume behaves over time. What's clear is that it doesn't always rise vertically as you'd assume. Even a light breeze at 1.5 meters per second can completely change the shape and direction of the cloud, pushing it several meters downwind before it disperses. Most standards and many design systems still assume that hydrogen will rise straight up because of the buoyancy. That's why point detectors are often positioned high above the equipment. In reality, that's not always what happens. If a seal or fitting fails under pressure, hydrogen can jet sideways or downwards, hitting the floor and then building up before it begins to lift. So the assumption that gas always travels upwards can leave gaps in coverage. This is why ultrasonic detection is such an important layer in the hydrogen safety. It doesn't depend on gas physically reaching the sensor like point detection does. Instead, it detects sound energy released by pressurized leak, so it reacts almost instantly regardless of wind direction, gas dispersion, or whether the leak is pointing up, down, sideways. In short, ultrasonic detection overcomes a really big weakness that conventional strategy imposes in outdoor ventilated environments, giving the reliable first line of defense before gas reaches flammable levels. So we'll look at regulatory requirements now, beginning with detection of the requirements for ISO 22734, which applies for electrolyzer systems. This standard recognizes gas detection as the key active protection method for preventing the buildup of an ignitable mixture, stating that ventilation should trigger at less than 1% hydrogen or around 25% of the lower explosivity limit. Where it becomes interesting is the wording around detection installation. The text calls for placement in the optimal location for the earliest possible detection, but doesn't give any definition of what that actually means. So while ISO gives the framework, it leaves a lot of interpretation to the system designer or the manufacturer. There's no clause saying how many detectors, what spacing, at what height. Only must comply with 6007929-1 and 2 for performance and selection. So this means the responsibility ultimately falls on the integrator or the safety engineer to justify the layout through fire and gas mapping and dispersion modeling. It's not always enough to say that detectors are compliant. They have to be placed where they will detect a release first. This section focuses on ISO 19880-1, which is the governing standing for hydrogen refueling stations. The standard requires both gas and flame detection as part of the mitigation measures and to prevent and control flammable mixtures. Gas detection systems should have a suitable set points tied to a control system or a safety system, so PLC or controller, meaning alarm should automatically trigger. Actions like ventilation or isolation. Flame detectors, on the other hand, ensures that if an ignition occurs, it's identified quickly enough to stop escalation, and the standard stresses that the system must be easily tested and verified in the field. Maintenance is also defined, so at least annually or frequently if the manufacturer requires, which is important for exposed outdoor installations where contamination or vibration can affect sensor performance. Also worth noting, this standard doesn't explicitly mention ultrasonic, but it does call for methods to prevent the formation of flammable mixtures. Ultrasonic fits perfectly within that because it detects the acoustic energy of pressurized leak long before it reaches a concentration where it could be ignitable. That's why most modern refueling stations do initiate a combination of ultrasonic, point and flame, and they provide early leak recognition, gas concentration monitoring and ignition response. This standard, the IEC 60079-291, in the ISO electrolyzer standard, defines the performance and construction requirements for flammable gas detectors, including hydrogen. It's the foundation for performance approvals that MSA has used for many years across all gas detection products, not just hydrogen. In Europe, any detector or controller that triggers a safety-related action, such as ventilation, isolation, or shutdown, must hold this certification. It confirms that the device is independently tested for response speed, accuracy, environmental durability. Not every product on the market meets this requirement, but when it comes to detector forms part of a safety system, it is essential. Our X5000, for example, carries FM performance approval under this standard. What's equally important is how detectors are installed or maintained. Even a certified device can fail to protect if it's positioned incorrectly or neglected. This is where proper design, fire and gas mapping, maintenance scheduling comes in. For hydrogen, that often means locating sensors where gas can accumulate at high points or enclosures. But yeah, in summary, it gives confidence that the detector performs as specified, but reliability comes from pairing compliance with sound engineering. Next is the IEC 60079-29-2, which builds on the previous standard by focusing on how gas detection systems should be applied in practice. It provides guidance on selection, installation, use, and maintenance of detectors, while 29-1 tells us how a detector must perform. This standard helps us decide where and how to place it effectively, generally. The standard highlights the need to consider gas behavior, air movement, and ventilation patterns, and to consult safety or gas dispersion experts who understand how this gas will behave in that individual environment. Hydrogen being light and diffuses quickly, accumulation zones often change with airflow or equipment layout, which is why, as I mentioned, mapping is so valuable. It takes variables and models how leaks would actually move through the spaces, helping us determine the right detector type and location. As I mentioned, even certified detectors aren't useful unless positioned correctly. But yeah, the main standard is that effective hydrogen detection isn't guesswork. It needs to be backed up by data, modeling, and good maintenance practices to keep that coverage reliable. So let's look at the layered approach that we have in our portfolio. So this slide sums up our safety philosophy with a really simple way to remember. Think of detection like human senses. So ultrasonic represents your ears, listening for the sound of a pressurized leak. Point gas detection is your sense of smell, detecting the presence and concentration of hydrogen in the air. And the flame detector is your eyes, identifying ignition if it occurs. So each layer works at a different stage of the event. Ultrasonic first picks up the leak. Point detection confirms the gas accumulation, and the flame detection responds if an ignition occurs. Together, they complete safety envelope rather than relying on just one device. These layers connect through remote monitoring and cloud systems, giving the operators live visibility of detector health, alarm status, and site performance. So you can monitor this across multiple stations anywhere in the world. You can maintain consistent safety oversight and respond if something does happen. So ultrasonic is the first layer of defense and designed for pressurized gas systems, in this case hydrogen. Instead of waiting for gas to reach a sensor, it listens for the ultrasonic sound energy that's created when hydrogen escapes under pressure. These frequencies, typically between 25 and 70 kilohertz, are far above what we can hear, allowing the detector to identify a leak within seconds, often before any measurable concentration forms. Each device covers 360 degrees with a detection radius of about 28 meters. And because it's listening rather than sampling air, it's completely unaffected by wind, dilution, or leak detection. This makes it ideal for outdoor or ventilated areas like compressors, manifolds, dispensers. The ultrasonic detector also uses an artificial neural network trained to recognize the normal background of a plant, so compressors, venting, depressurization, even helicopters, and it knows to ignore them. It only reacts if a specific acoustic pattern of a gas leak occurs, which is why we can offer fast detection without false alarms. So it is our ears in the system listening unaffected by conditions, giving you the earliest sign of a potential leak. Point detection forms the second layer of our strategy to give this sense of smell in the system, as I touched on. We use two main types of technologies here: catalytic bead and electrochemical. So catalytic bead detects combustibility. They work by oxidizing hydrogen on the surface of a heated bead. That reaction changes the bead's temperature and therefore its electrical resistance. The detector measures the change and converts it into a signal proportional to the gas concentration. So this is expressed in a percentage of lower explosivity limit, or LEL. Electrochemical, on the other hand, are designed for very low-level hydrogen measurement in the parts per million range. They work by creating a small electric current as the hydrogen reacts at the sensing electrode, and the strength of that current is relatable to the gas concentration. So in terms of placement, we put ppm range sensors close to potential leak points or enclosures where there might be a small buildup that could indicate an early fault. LEL rather is positioned higher for broader coverage zones to capture larger leaks or accumulations that could approach the flammability limits. So these two provide the early leak detection and confirmation of the hazardous concentrations, making sure the system reacts proportionally before conditions become unsafe. Hydrogen flames are almost invisible to the human eye because they emit very little visible light, almost none sometimes, and only a small amount of thermal radiation, which is why UV and IR flame detection is essential for hydrogen applications. The FL500H2 combines ultraviolet and infrared sensors that work together to identify hydrogen flames. When hydrogen burns, it produces a distinct flicker pattern across the both UV and IR wavelengths. The detector is constantly analyzing this signal. When it matches the characteristic frequency and the modulation of that hydrogen flame, it confirms it as a genuine ignition event. The advantage of using both the UV and IR channels is that the detector can distinguish real flames from environmental light sources. So the UV sensor is sensitive enough to detect even the small hydrogen flame, while the IR sensor verifies the flicker pattern. Sunlight and hot surfaces emit steady, constant radiation, where a flame produces rapid, irregular changes. By recognizing that difference, the FL500 avoids false alarms and focuses on just finding that hydrogen flame. Connectivity is what turns detection systems into a source of operational insight. So with our cloud connected infrastructure like the MSA grid, each detector continuously feeds live data into one platform. This means operators can see when and where the leak has occurred, the concentration at that specific time, and how readings have trended, whether in ppm, LEL, across the site. It allows the operational team to review average exposure levels, confirming the alarms responded correctly and ensuring compliance is reporting based on actual performance data and not just manual checks. So the detectors are the eyes and ears and your nose in the field, but the connectivity gives you the intelligence to understand what's happening. So let's look at a real case study. I think this would be quite interesting for you guys. So before we get into that, let's look at when we're designing a fire and gas system for a hydrogen plant. First of all, we have to look at a plant's evaluation. So before choosing any technology, we need to understand the process layout and the site's physical characteristics. So where the electrolyzer, the compressor, storage vessels, manifolds, and the end-use equipment are located. Each introduces a different level of risk, from low pressure process leaks to high pressure releases that can disperse and ignite very rapidly. It's essential to consider how hydrogen behaves in that specific environment. So factors like the pressure, gas state, and whether the area is open or enclosed will determine how the leak spreads or accumulates. The structural features like the pipes, walls, roofs can affect ventilation and create traps. The goal at this stage isn't just the installation, it's the understanding of the process, the gas behavior, the leak sources, so that detection can be designed around the plant conditions and not just assumptions. Once the plant layout and main risk areas are understood, the next step is selecting the right detection and placing them where they're most effective. Ultrasonic are used in high pressure zones like compressors and manifolds and storage vessels, ideal for outdoor areas where wind or obstacles could stop gas from reaching the point sensor. The point detector, catalytic or electrochemical, cover areas where hydrogen might accumulate, such as pipework, canopies, enclosures. Dual or remote setups improve coverage and simplify maintenance. 100% LEL sensors for the larger leaks, and then ppm sensors for the early detection near joints and seals. Flame detectors are aimed at ignition sources, high-risk equipment, recognizing the hydrogen's hidden unique UV-IR flicker for rapid visual confirmation. At this stage, we're defining the system's architecture, combining the technology, overlapping coverage, and ensuring that every credible leak or ignition source is protected by at least one detector. So let's consider a real-life example of a FGFD system for a hydrogen refueling station. So I'll dive right into it. So starting on the left in the storage and compression areas, the green markers, as you can see, show the ultrasonic detectors placed near compressors and cascade racks. These are the highest pressure points with the greatest release energy, and the ultrasonics provide immediate detection regardless of the wind and leak direction, as I mentioned, within that 28-meter coverage radius. The yellow markers are point detectors operating in the LEL range. They're used here because hydrogen is stored and handled at very high volume and pressure, so detection needs to focus on concentrations approaching flammable limits rather than trace levels. They're positioned across compressor faces and under pipe racks where gas could collect, feeding real-time concentration data and automated actions into the system. The red markers indicate flame detectors. They're mounted on corners, aimed at the compressor skids and vent terminations to maintain a clear view of ignition sources. Each detector overlaps another's field of view to increase the coverage and reliability, so there's no gaps. In the tube trail areas, an ultrasonic detector sits by the connection manifold to catch any high pressure leaks during coupling or blowdown, with a flame detector watching the full trailer lane and to identify ignition quickly. At the dispenser island on the right, just below the blue part, ultrasonic detection covers the dispenser from fast jet leak detection. A point LEL sensor monitors under the canopy where gas could accumulate, and a flame detector faces the nozzle and the vent stack for optimal confirmation of the ignition. And finally, all signals feed to the Suprema Touch controller, which links the system together, issuing alarms, isolating equipment, and shutdowns, recording every event for traceability. So each layer is defined in this scenario: ultrasonic detecting the leak instantly, point detectors verifying the gas buildup, and the flame detectors confirming ignition, all connected through the control systems. Okay, let's consider an electrolyzer facility now. So this layout shows how we've applied detection around an electrolyzer installation operating in an outdoor environment where both hydrogen and oxygen are present in parallel. They're both being produced by the electrolyzer as it splits water into hydrogen and oxygen. The blue detection is the ppm range hydrogen sensors positioned close to each stack. They provide early warning of small leaks around fittings or seals before the gas can reach flammable levels. The red detectors are LEL sensors placed slightly higher and around the purifier and the recooling areas where hydrogen leads the stack at roughly 30 bar. These monitor for larger accumulation approaching the lower explosivity limit and provide the set point for automatic control actions such as isolation or ventilation. The green detectors measure oxygen concentration because both hydrogen and oxygen are generated in the same process area. These sensors ensure safe atmospheric conditions and help prevent enrichment or displacement that could create asphyxiation risks. The yellow detectors in this scenario are ultrasonics, so installed around the manifolds and the gas outlet line to detect any high pressure hydrogen release acoustically. They respond within seconds and provide obviously the earliest alarm that there's been a pressurized leak. And the red triangles are flame detectors pointed towards the ignition sources like the stacks and transformers. Transformers being a big one, so obviously a lot of electrical equipment there. And you've got a flammable gas and hydrogen, so that's a key ignition source right there. The purifiers, they identify the hydrogen as near invisible flame within seconds, of course. All these signals are managed by the controller, which coordinates the alarm logic and shutdown. Together, these gives the full coverage across the electrolyzer process. So the ultrasonic for the high pressure, LEL and ppm on this occasion for the gas buildup, oxygen monitoring for the atmospheric safety, and the optical flame for the ignition response. So as you can see, it's slightly different to the refueling setup because you've got the introduction of oxygen and then smaller leaks at lower pressure, which is why the strategy changes dependent on what type of hydrogen system you're designing. So to conclude, what sets MSA safety apart? So in terms of how we're different in terms of the hydrogen detection, not just our product range, but what the engineering that underpins all of it. So our ultrasonic detection is powered by an artificial neural network, which is an AI tool trained on thousands of real-world scenarios. So it's learned to recognize the distinct sound profile of a hydrogen leak while ignoring the typical sounds of an operating plant. So compressors, venting, helicopters. So it gives a near instant detection with really good stability and minimal false alarms. Our catalytic bead sensor features a mechanically reinforced bead structure that resists vibration and mechanical shock. What does this mean? It means it's reliable around compressors and refueling systems, as it gives a much longer service life. And our FL500 UV-IR flame detector, which we have covered earlier, uses a dual optical channel to confirm the flicker pattern of a hydrogen flame. It's built to remain unaffected by sunlight and maintaining a high immunity to false alarms in those outdoor environments. And finally, our MSA grid ties together all of this through cloud connectivity, giving operators full visibility into detector performance, alarm trends, and site conditions across multiple facilities. So I guess our differentiation isn't just about detection, about intelligence, resilience, connectivity, and delivering hydrogen safety that's proven. This slide brings everything together and shows how MSA's approach aligns with the hydrogen safety standards. The combination of fixed gas and flame detection, point and optical technologies are consistent with the requirements set out in ISO 19880-1 and ISO 22734 for preventing the formation of ignitable gas mixtures and ensuring a timely detection of fire or leakage events. So our layered approach, developed in line with the IEC 61508 and 61511, ensures that detection coverage is based on functional safety principles and practical risk assessment. The focus is on identifying leaks at the earliest stage, isolating the source quickly, and maintaining safe operation throughout fueling or production. So as hydrogen applications regulations continue to evolve, our system design philosophy already meets the intent, using complementary technologies and control integrated and connected monitoring to prevent hazardous gas accumulation and escalation. To ensure MSA's layered detection strategy ensures full compliance with the intent of ISO IEC standards by enabling early detection, fast intervention, and continuous protection across hydrogen infrastructure. So thank you all for listening. Would now join live and welcome any questions. But if you want to reach out, we have our hydrogen email there. We'd be glad to answer any questions. Okay, thank you.
Hi everyone, and welcome to our Q&A session with Jack Samways from MSA Safety, whose presentation we've just watched. Welcome, Jack. How are you today?
Very well, thanks, Callum. Thanks for having me. Hope the presentation was useful.
No, great stuff. Thank you very much, Jack. So let me start by thanking you for that really detailed and interesting presentation, providing insights into hydrogen safety and exploring best practices for detection system design. It was really fascinating to hear a little bit more about the latest technological advancements that are helping to support the safe expansion of hydrogen applications worldwide. So really appreciate your insights. Thank you for that. Now, we're going to move on to the Q&A session now. If you've got a question for Jack, please send it in to us now using the chat or the Q&A tabs, which are on the right of your screen, and we'll get through as many as we can. Jack, the first question that I've got here is asking, based on hydrogen's properties, can the same product and or technologies be used for detecting both hydrogen and other gases?
Yeah, good question. So there are certain technologies which are applicable for other gases. So catalytic bead sensors, they will react to other flammable gases as well as hydrogen. But that's really for larger leaks for LEL percentage measurements. So that's why it's important to have both electrochemical and catalytic. So as mentioned, catalytic is mainly for LEL percentage leaks, so larger. Electrochemical is for ppm and is specific for hydrogen. So you'd have those closer to where you've got hydrogen gas stored or being produced, and that will let you know of the ppm level leaks to confirm that is hydrogen. Then again, the catalytic can then be there for larger leaks as well as other flammable gases. But there are other technologies like IR sensors that hydrogen doesn't react to IR sensors, so it wouldn't be suitable in that scenario. So yeah, there is specific products that are suitable for hydrogen and others that are more for hydrocarbon uses. But it's all about application-based knowledge, really.
Great. All right. Thank you very much, Jack. And can you explain when catalytic bead or electrochemical sensors should be used for point detectors?
Yeah, so I touched on it slightly in the electrolyzer slide, where you've got an electrolyzer stack and you have ppm sensors, which are electrochemical sensors, closer to the stack where you're looking for smaller ppm leaks. And then you'd have LEL, which is catalytic, much further up. Another key factor is that catalytic bead sensors are better for harsher environments, and it's got a robust design. So any sort of vibrations that are caused from compressors or any sort of thing that can happen on a larger plant, that's where you'd have catalytic to ensure that it's not going to be reactive or need recalibration from having those harsh environments.
And as a kind of follow-up to that, Jack, we've had a question come in asking regarding point sensors, are you able to explain the pros and cons of electrochemical versus ceramic?
Yeah, so the key thing with the electrochemical is the fact that you can measure in ppm. It's really sensitive to those really low concentrations as opposed to ceramic. So I think that's the key thing. So having that really close to those smaller leaks to ensure that it's specific to the hydrogen gas that it's measuring, and that those alarms are going off before a larger leak can formulate and those vapor clouds can approach the lower flammability limit.
Great. Thank you very much, Jack. And can you explain why combined UV-IR technology should be used for hydrogen flame detection?
Yeah, so when it comes to a hydrogen flame, the pattern of the flame is, of course, is invisible, as I touched on in the presentation, but also it flickers in both the UV and IR wavelength. So it uses independent sensors to ensure that the flame that's being produced is flickering in both of them. In comparison to the sun's radiation, which is more of a constant radiation across it, so it will be very very uniform and constant. So the UVIR technology knows to ignore that and just focus on the flicker. And that's how you reduce the false alarms and the quick response.
Okay, perfect. Thank you, Jack. We've got a question here that's asking about the life cycle of MSA's gas and flame detection control centers. Are you able to provide us with any information about that? And they're also asking if you have any centers compatible with the latest versions of Windows.
Windows. I'm not sure on that question. So, but the life cycle of the gas detectors. So, for example, the ultrasonic gas detector actually has a self-test, almost like self-calibrating feature to it. So every 15 minutes, it will impulse a ultrasonic sound to ensure that it's working effectively. Similarly, the FL500 has a self-test feature. We call it COPM. And that ensures that the UVIR is working effectively and that the screen's not fogged up to ensure that the flame is being detected. But the point detection can have lifetimes of up to 3 years. So obviously you need calibration, but in terms of the actual sensors, we've had sensors out in the field for a really long time, over 3 years. But I'm not sure on the Windows question. I'm not sure what he's trying to get to at that point. So I'll have to follow up with him.
Yeah. What about the final question that we've got here about asking, are there any mobile gas detectors to be used with FPV drones, for example, in tank farms or dispatch terminals?
Yeah, so we're a big company at MSA Safety, so we do have different parts of the business. So I work on the fixed side, but we also have a portables business, which do have hydrogen sensors. So can certainly we will be able to supply those applications on drones, but yeah, it wouldn't be my specific side. But I'll have a colleague who'll be know a lot more about that and can pass their details on to Urgeny.
Perfect. Thank you, Jack. Another question we have here is asking, is there any general guidance for the positioning and quantity of detectors that should be used? So, for example, for a 20-meter square area, what number of detectors would usually be required?
Yeah, so I suppose this is a question we get asked a lot. There's actually no rule of thumb whatsoever. Every plant is completely different. It's got its own features, so its own compressors, own refueling stations or electrolyzers, and therefore its own leak paths as well. So they'll have a varying amount of valves and leak points and ignition sources as well. So some will have transformers, some will not. Some will have a larger amount of electrolyzers, a larger amount of gas or flow rate. So every plant is completely different. So we treat every plant differently as well when we're laying out a fire and gas mapping study. So the best way forward is to have the layered approach, but to verify the placement, the quantity, and the types of detectors using fire and gas mapping. So you can use dispersion modeling to replicate a leak scenario. So you can basically figure out where a leak is most likely to accumulate, whether it's a confined space or anything like that. So that's how you can verify where you're placing your detectors and how many and which types. So that I'd recommend sort of using fire and gas mapping to verify that.
Great. Thank you, Jack. And another question we have here is asking if you offer in situ H2 and O2 analyzers for electrolyzers.
So we do have an analyzer company. That is another part of the business, not my specific. So we kind of focus on the gas detection, but yeah, certainly be able to follow up with them with that part of the business that controls that side.
Great, thanks, Jack. Another question we have is asking, why do you consider ultrasonic detection to be better than other technologies?
Yeah, so I wouldn't say ultrasonic's better. I mean, as I mentioned, the main focus when it comes to hydrogen systems specifically is the layered approach. So I talk about ultrasonic being in the ears and the point being the smell and the flame being the sight. So there's no so much better. It's really for specific applications. So where Observer is the most unique and the most suitable for these applications is outdoor environments where you've got wind conditions blowing gas clouds away, and when you've got a high pressure gas. So, you wouldn't use it for atmospheric gas pressures, but where you've got a high pressure gas, that leak first occurs and emits an ultrasonic sound from that high pressure gas leak. That's where ultrasonic's so effective, where you've got wind conditions that can create gas clouds to be really unreliable. Ultrasonic takes that all away. It understands what is a typical sound of a hydrogen plant. So a typical sound would be a compressor, helicopter, depressurization, and it knows to ignore all of that and just focus on that ultrasonic gas leak that's occurred from a high pressure fitting or gasket that fails and causes that initial gas cloud to formulate.
And on the topic of technology that's better, Jack, what technology would you suggest is the best for hydrogen?
As I say, this again, similar to my last answer. There's no sort of best. I mean, as I mentioned, the layered approach is will give you the best chance of that leak going detected and ensuring you're not getting up to the flammable areas and therefore ignition occurring near an electrical component. So what I'd recommend is having ultrasonic for the first layer, both ppm and LEL detectors for the point to measure the gas clouds concentration, and then for sure having flame detection so you can see the invisible flame. I mean, it's so dangerous not being able to see it, especially. So the FR500 confirms that with the false alarm immunity and protection from that hydrogen flame that could occur. So yeah, there's specific point detection, I say, with the electrochemical that's suitable for hydrogen, but a combination of all of them is the best way forward. And then completing that all with a controller that links to ventilations and shutdowns and alarms. So it's a full system would be the best way for hydrogen because of its unique properties and the dangers it has from the properties of that gas.
Great, thanks, Jack. So we've got a couple of minutes left, so maybe time for one more quick question.
Of course.
I think you touched upon this in your presentation towards the beginning, but one of the questions we've got here is asking, have you considered adding an odorous gas like LPG in small proportions?
Yeah, so I did touch on it at the start of the presentation, but yeah, when it comes to hydrogen, unfortunately, you are not able to add any odorants whatsoever, especially from the safety side of it, because it's such a unpredictable gas that a combination of other gases can cause it to ignite, for example, or cause a combustible gas mixture. But also because of the fuel cells in vehicles or trucks, buses, trains, whatever it may be, they've got a requirement for a really, really high purity of hydrogen, often 99.99%. So adding an odorant would therefore make that gas impure. So if we were then to add an odorant to give it a smell, then it would go down to the end use and then go into a vehicle. That wouldn't be suitable for that fuel cell. So when you look at the wider picture, yeah, odorant unfortunately isn't a use. It would make obviously everyone's lives easier, but yeah, best way forward is to use our gas detectors.
All right, Jack, thanks so much for taking the
No
time
worries.
to answer our questions for us today. Really appreciate it.
Of
If you do
course.
have any further questions for Jack and the team at MSA Safety, please head over to their virtual exhibition booth where you'll be able to chat with company representatives and find out a little bit more about what MSA Safety are able to offer. I'd also like to encourage everyone to read MSA Safety's recent technical articles that they have prepared for the spring and autumn 2025 issues of Global Hydrogen Review magazine. You can pick up your free copies of those issues over at our virtual exhibition booth. So thanks again, Jack. Really appreciate your time.
No worries, Callum. Thanks. Cheers.